So, we do start? Let's start. He's going, he went to search for mission.
Well, he just finished the lecture on cost structure, but he went to office and
Okay, no, but Anton, what about Anton? He was here.
He was here, then he went out, repeat escape.
Is that his notebook or?
Yes,
yes, it is.
So he disappeared. Oh. So now we get started.
We cannot start with that.
No. We are very happy to have the second lecture by Sylvain on ODE and correspondence and affine Golden models.
Yes, great. Well, thanks again for the introduction. So yeah, this is the second lecture about this ODIM correspondence. And in particular, in this second lecture, I want to talk about a slightly more advanced and more recent topic, which is called affine Godin models, which is also where I myself work a bit more on. So yesterday we saw some correspondence, then some example of this ODIM correspondence, which relates ODEs to some integrable models, and more precisely integrable conformal field theory in 2 dimensions. And in particular, in these integrable models, there were some local charges. So these, they were taking the following form. So there were integrals over the spatial variable of some densities. So the way this works is that we had a certain CFT that was described by a certain Carroll algebra with some fields satisfying some commutation relation, and we were building some local charges by taking some normal ordered product of fields and integrating them over the spatial variable in such a way that in the end these should all commute one with another. And part of the ODIM correspondence was to explain how you can get the eigenvalues of these local charges encoded in some property of integrable models. And yesterday we saw the example of the KdV local charges, which were built in terms of just the stress energy tensor. But so today I'll show more examples, and in fact a quite large class of examples called affine Godin models, where the fields will be a bit different, and explain how then the local charges are extracted. And well, in particular what we saw yesterday is that the eigenvalues of these IP, these local charges, at least in the case of the Virasoro, of the KdV charges, they were encoded into the WKB expansion of some specific ODE. And in fact, they were contained in the WKB expansion of the quantum period of some ODE. And what I will explain now is that, in fact, this is quite more general. But in particular, yesterday, we had to choose a specific ODE, and it was not so clear how to get the right ODE to match a corresponding integrable model. And that raised the question whether we can do something a bit more systematic. So a more systematic approach to this ODIM correspondence. And also another natural question is, what's the role of the ODE variable? So yesterday, this ODE, it was a certain complex variable z, but it was not clear at all what was the role of z. Z did not seem to play any role in the integrable model part. And so it was not clear what was its origin. And in fact, I want to explain that we can get something at the same time more systematic, and in which we get some origin of this ODE variable directly at the integrable model side through this idea of affine Godin models. And that will be my main topic for this second lecture. And just for a few references to the idea of these affine Godin models, this is something that dates back from Fagin and Frankel in 2007. And in particular, their main conjecture was that this whole story about ODIM was in fact just some incarnation of the Langlon's correspondence for affine groups, which is part also of what I will explain. And so most of what I will say is based on ideas coming from there, and in particular, some things that we developed a bit later on. So this is myself with Benoit Bicedo and Charles Young, where we made a bit of progress in this direction, and also more recently, Gleb Kotosov, myself, and Joop Teschner on some of these aspects. Okay, so the plan that I will follow is in fact quite simple. I will start by recalling some things about WKB expansion. So I said a few words yesterday, but I want to go a bit more in the details of this. And in particular, knowing the structure of this WKB expansion will be useful later on as a guide for the integrable model part. And then I will discuss then the construction of these affine Godin models, in particular the construction of local charges in there. And finally, I will describe their spectrum and how this ODIM correspondence works in that case. So let me start then with WKB expansion. So I'll consider some ODEs of the following form. So just a few remarks compared to yesterday. So now I write ODEs with some potential here. There's a small difference with yesterday, which is now I in fact also allow the potential itself to have a correction in h bar. Here I put just one correction of order h bar squared, but we could have even a higher order tower. But I will need this correction here later on, not the other ones. Whereas yesterday, in fact, I only had the V0 term. And the other thing is yesterday I had some eigenvalue. Here I consider it as part of the V0, right? And so from there, if we want to do the WKB expansion, we do some ansatz for our solution. Exponential of SH bar ZDZ. So we write our solution in terms of another function S. We plug this back in and we get some equation for S, which is some Riccati type equation. And then we search for this Riccati solution of this Riccati equation as a power series in H bar. And we see that this is compatible with something that starts as order 1 over H bar, with the corresponding coefficient being the square root of V0Z. And then we get some higher order correction. So we start with order 1 over H bar, and then the corresponding, this is purely algebraic, then it corresponds to the square root of this V0 of Z here. And then we get higher order corrections, which are now positive odd powers of H bar. And here, just for convention, I put some prefactor, which also have a square root of V0 and some specific power of V0. This will be useful later on. And then I get this new object SP of Z, right? And the idea is that I can put this formal series expansion inside of my Riccati equation, and I see that this is compatible, and I just get some recursion relation for my SP of Z here. And this will then allow me to get all of them. It won't be a converging expansion, so to really get actual solution, I would need to do like Borel resummation. But for me, in fact, it will be enough to just consider the formal expansion, because I'll be interested in just this type of coefficients here. And so to give a bit an example of how this works, so if I look at the first coefficient, S1 of Z, this will look like this. So it will start with something with the V1 of Z, and then the following term, which I express in terms of an object phi Z, which will be quite useful for me, which is just the logarithmic derivative of V0. So this is V0 prime Z over V0 of Z. Right, so I find this expression for S1, and then if I go on, in general, SP of Z will be a differential polynomial in V1 and this phi here. Right. Okay, and in particular from now, I can define then the quantum period, which I'll take to be pi gamma h bar, and I'll take it to be the integral of this S here over some contour gamma, and the gamma, I will think of it as being part of some specific homology. I won't give a very precise, very completely rigorous definition, but essentially I want this gamma to be contours with a single branch of the square root of V0z. So, yeah. Yeah.
Keep pressing.
Keep pressing.
Keep pressing.
Okay, it's, I see. No, too much.
No, keep.
You see.
Aha, okay, good.
Okay, here.
That's fine, yeah. Good. So here I do the integration of a gamma. So here I think of gamma as being a contour in the z-plane. But I cannot take any contour because when I do in my S here, I will have some square root of V0, so I need to be a bit careful about this. So I want my contours essentially to have a single valued branch of this square root on it, right? So for instance, if I go for a branch cut once, I should go through another branch cut another time, at least, so that I come back to the same branch. So maybe in the simplest case where this V0 of z is itself single valued, essentially I'm working on the cover here, and I want to find things in the cover. And a slight comment on terminology as well and convention. In fact, this is not exactly the quantum period. In general, the quantum period, I would remove the 1 over h bar, so that this is something that starts at h bar 0, right? To avoid having h bar everywhere in my solution, in my expressions, I just remove it. So this is h bar times the true quantum period of h bar, if we're being really correct. Okay, and something that will actually be quite important for what I'll say next about the integrable model is the notion of gauge transformation of this. So I won't explain all the details on where it comes from, but the idea is that if I have a second order ODE like this, I can always rewrite it as a first order ODE in a vector psi prime, where now I have a connection acting on it. So a 2x2 matrix, essentially, connection acting on it. And then in that case, I have a notion of gauge transformation, which is I can do essentially z-dependent change of basis of my vectors, and that will transform the connection in some way, but that gives, of course, a purely equivalent ODE. And in particular, I can do these kind of gauge transformations in a way that change the ODE, and that will in the end change this WKB momentum S, but which in the end will be equivalent, an equivalent ODE. And more precisely, the way this type of transformation acts on S is as follows. So I get a new momentum SV h bar z, which is the initial one shifted by a total a z derivative. And here this v is then my gauge parameter, essentially. And in particular, I see then that the period pi gamma of h bar is invariant, and my gauge transformation that sends S to SV, because I'm shifting it by a total derivative. So if I integrate over a closed contour in the end, that will give 0 if I have proper boundary conditions, and I will say a few words about this later on. And so in particular, we see that the quantum period, which essentially measures some kind of monodromy property of this ODE, they're equivalent if I do a gauge transformation. And so I will be able to just I can use this kind of freedom to transform a bit my momentum. So this is at the level of S itself. If I now take my V and I do a power series expansion in h bar with only the positive powers here, so similar to this one, I get then a transformation of each of my component SP V of Z And this will be as follows. So I get a shift by dpz vpz, where I introduce what is called a twisted derivative, which this dpz of f, which acts on a function by the standard derivative plus a shift 1/2 minus p phi z f of z, where phi is this function that I introduced here, the logarithmic derivative of v0. So that just comes from saying I take this thing and I say I shift the whole thing by a total derivative, but then I want to see the effect on the SPZ itself, so I need to essentially factor out the v0z, and I get a contribution coming from the derivative that acts on the v0z. And that gives me this twisted derivative here. Yeah?
This v, do you write the Gauge transformation as e to the v or something like that?
So this would come essentially, so in the matrix language, it would come from essentially exponential of v in some Cartan element, essentially. But now here, I really think of v as just a function, which is which I write then as a sum of v0z p minus 1/2 vpz h bar to p minus 1. Right? I do a. Sorry? Yeah, and essentially then writing the effect of the derivative of this and see how it shifts the SP defines the SP, this twisted derivative in this way, right? So far, so good? Yeah. Good. And in particular, then I see that the property of gauge invariance that I had, if I write it as in terms of just the h bar to the power 2p minus 1 coefficient, essentially in the end that amounts to the following property, which will be quite useful for me later on. I'm essentially saying that these type of integrals here are 0 for all f, for all function f and all gamma in h. And so the way this works is almost by definition, this thing here, what it is just a total derivative where I put the v0 inside of the derivative, right? That was essentially my definition of what was this twisted derivative. So now I get an actual standard derivative with respect to z, and so when I do the integral of a gamma of a closed control, this will give 0. And this is where I need to put some restrictions on f and on gamma. So f, I'll take it to be just a meromorphic single-valued function. And then gamma, I take it to be in this twisted homology, which means I have a single branch. And that is what ensures that in the end I get 0, because I start at some starting point in gamma, then I come back to the same point, and because I have a single branch of my v0, this will get back to the same point without monodromy, and I do have a cancellation. So that's why we work with these specific choices of contours H here. And in fact, this property, it will be quite useful later on when I define these affine Godin models. So, which is in fact this next step I will go on. So let me maybe ask at that point if on the WKB part there are questions. Then in that case, let me then go on with the affine Godin model. Constructions. So very roughly, the idea is we want to have a definition of an integrable model where the construction of in the construction of the commuting local charges, we will in fact see a role played by this z, which in the end will be the ODE variable. And very heuristically, in the end, the main idea is that the local charges themselves, they will be built as some integrals. So some integral of a dx, the spatial variable, but also an integral over the dz and these contours gamma of something. And this in fact makes sense because in the end we expect the eigenvalues of these objects to be encoded into some quantum periods, which are themselves integral of this form. And so in fact, what in the end we'll get from this affine Godin model construction is that it's not only the eigenvalues that are integral of the z, but in fact the charges themselves, the operators themselves will be eigenvalues of the z. Right. And that will be essentially the main thing I want to explain now, how that works. So this model, it depends on a certain number of parameters, which we call the punctures, Z1 up to Zn in the complex plane. And so essentially what I'm doing is I'm looking at the complex plane, which I think of the Z plane here, this variable Z, and I have some number of marked points, Z1, Z2, up to Zn, which in the end will be some parameters of my theory. Right? And now to define the model, the first thing I need to do is define the algebra of fields in which I'm working. So recall yesterday when we were doing the Virasoro, the KdV charges, we were working in the Virasoro algebra with just one field, which was a stress energy tensor. Now we'll have something in fact quite more general, where the fields are so-called Kac-Moody currents. So written like this. So these are field GARX. So X is the spatial variable, and then I get two indices. A is a Lie algebra index, and so in fact there's something that I didn't say is that here I'll look at affine Godin models based on the algebra SU2, and in general I could have higher rank affine Godin models, but here I'll focus only on these SU2 ones. And then I get here a Lie algebra index, then which I think of from 1 to 3, so it's just an SU2 index. And then I get a R index from 1 to N, and this one is a puncture index, right here. And so now the idea is essentially to each of my puncture, I attach a Kac-Moody current J1x, J2x, Jnx, and each of them is an SU2 valued field, right? So to define exactly what these currents are, I need to specify what are the commutation relations, or if you want their OPEs in the language of CFTs. And so I need to look at the commutator at two different values of space, here x and y. And here I find the following, 2 pi delta Rs. So first of all, I have a Kronecker delta in RNS, which means that Kac-Moody current attached to different punctures, they commute, they're independent. And then at a given puncture, I get the following algebra, epsilon ABC JCRX. So that would be essentially the commutation relation of SU2. This is the completely skew-symmetric tensor, so that's the structure constants of the Lie algebra SU2. And I essentially have some kind of field theory version of it, which means that in addition of this, I will have in fact a Dirac distribution centered in X minus 1.
What is this letter for GE?
Sorry. S, sorry, yeah. Yeah, so these A and B are Lie algebra indices, these R and S are punctures indices here. Yeah. So yeah, this is like some kind of field theory version of SU2, where now I have a Dirac distribution at my centered at my spatial coordinate, coinciding points. And then I get a central extension that take the following form, delta AB, delta prime, x minus y, where this KR here is what is called the level, which is a parameter on which this algebra depends. At the moment, I'll think of this as just any complex number, but later on, if you want to consider a unitary representation, you need this kr to be a positive integer. But just algebraically, I could, for the moment, define it for any value, right? And so in the end, the parameters of my theory, then I get two types. I get the punctures that are, so the position of these punctures, and I get the levels of the Kex-Moody current attached to each of these. And that defines for me the algebra in which I work.
But the J's are computed where? In the G, or
sorry?
What? The current, the X variable is where?
So the X variable is not this plane. This is now a new variable. So Z and X are completely distinct, right? X is really my space variable of my CFT. That's the actual physical spatial thing. And so what I'm saying now is I have fields that depend on this X. I'm working essentially here on a time slice, so I have to give an X on the cycle. Whereas the Z is a purely auxiliary, and in the end will be kind of a spectral parameter for my model.
So this Z plane still doesn't.
So for the moment, it doesn't seem really related to the Z-plane, except that I said that I think of each of these current attached to a puncture. But later on, we will see why it's kind of natural to think of these, because later on, Z will play a role. That comes in a few equations, essentially. Right? Other questions? Okay. So before, in fact, I come to this Z and the interpretation of Z here, there's one thing that I can say about exactly what it means to have these Kex-Moody currents. So recall that yesterday when we had the stress energy tensor and we want to extract it actually what was where the operator is acting on the Hilbert space of the CFT, we had to do a mode expansion, right? So we were looking essentially at a Fourier decomposition of the fields. And yesterday we got the standard Virasoro modes. But so now I can decompose also my Kex-Moody current in terms of some modes, GARN. So now it starts to be a lot of indices. This is still the algebra puncture, and I have this loop mode N, which come from the Fourier decomposition. And then I can translate the commutator I had here in terms of X and Y as a commutator of my modes. And I find the following. So delta RS, I epsilon ABC JC of R. So what happened is that in this part here, in this kind of SU2 type relation, the idea is that the mode N with the mode M will close in the mode N plus M. And then in the central extension, I get the following delta N plus M0. Essentially, this N here, it comes from the fact that I have a derivative of Dirac. So when I derivate Fourier series, I essentially get an N back, right? And something I didn't say is the delta AB here, essentially the way I should think of it is the killing form on SU2. I'm just working on an orthonormal basis here.
So the X are on the circle.
The X here are on the circle, so I'm really thinking of a CFT on a cylinder, right? And so I do this decomposition on the circle, and then I translate my commutator here to a commutator of the modes. Right? And this is, in fact, a very well-known algebra. So more precisely, I get here n copies of the so-called affine algebra SU2 hat K. So the affine algebra, that would be essentially just what's inside of my parentheses, of my brackets here, right? It's an infinite dimensional extension of SU2. So the way we see this is if we focus on the zero modes, this part vanish, and this we see it closes in the zero mode, and this would be just the standard SU2 for the zero mode. But now I get an infinite dimensional generalization of that, depending on these loop modes with this type of algebra here. And this is something that we...
There you have kappa with some index.
Yeah, so this would be just for one copy. This would depend on one level k. But now what I'm saying is that I get n copies of this, and all the copies can have different levels. Right, so that's why for each puncture, essentially, I get.
This is a kappa error.
This is a kappa error, R. Right, so my levels, they were different for each of the copy. And so I don't need to have like the same level at each puncture. So they're part of the parameters defining my theory as well. Right. Okay, about this, yeah. And so this is in fact what these are called affine Godin models. So Godin models, they were initially introduced as kind of spin chain associated to finite dimensions. So here we would associate like a copy of the standard just finite dimensional SU2 to each of the puncture in the standard finite Godin model. And this would be like a system of spins in interaction. But now we do a version of it where we have an affine Godin model where at each copy we attach now a current here. So that's why now instead of a spin chain, we now get an actual field theory, right? Because we have this infinite number of degrees of freedom attached at each puncture. Okay. So now we get, in fact, to one of the, yeah.
So the plane is the plane of the Godin model.
The Z plane will be the plane of the Godin model, and that, in fact, will be exactly what I'll explain now. Because the key ingredient in all the construction here will be to introduce an object which I'll call essentially the Godin field, gamma AZX, and which is defined as follows. So JARX Z minus ZR. So now, instead of having n independent Kac-Moody currents, I want to gather them all into one unique object. And this is where I introduce this parameter Z. And essentially, I think of this as some kind of generating function for my Kac-Moody current. So it's a meromorphic function if Z with punctures exactly at the ZR. So that's why I call them punctures, right? They're the poles here of my gamma. And the corresponding residue is my Kac-Moody current. Right? And so now, instead of working with all these Kac-Moody currents separately, I will think of them as being part of one unique object, which now depend on Z and X. And in the end, the Z will be the same Z as what appears in the ODE. And in particular, the first result that will be quite useful is that I can translate the commutator I had earlier for the Kac-Moody current into a commutator for this new object. So once again, I'll have a lot of indices and dependence. So A and B are still Lie algebra indices. Z and W are two different values of the spectral parameter, right? This new parameter. And X and Y, they're now spatial. They're still spatial things, right, on the cycle. And now it turns out that all this can be rewritten in a very compact way. So this part here in the delta X minus Y, I can rewrite it as gamma CZX minus gamma CWX over Z minus W. And so that's, in fact, a very nice part. When I do the computation from there, I initially get something that depends on all the Z and ZR and so on. And in fact, I can always rewrite it very compactly as just gamma at Z minus gamma at W divided by Z minus W. In particular, what I see now is this becomes independent of the number of punctures that I had and their position. So I get some kind of universal algebra that will work for all my affine Godin models the same way. And so that's just a small computation to do. And then that was for the delta part. The delta prime part essentially works in a similar way. Can you see if I'm down there or, yeah? Yeah. And now I get phi Z minus phi W divided by Z minus W, where, so this will be kind of my key formula, where I introduced a new object. I introduce what I'll call the twist function. phi z, which is the sum of the kr over z minus zr. So this is exactly the equivalent of my gamma. So what was gamma for my X-magnetic current? Now I have something similar, but which is some kind of generating function for the levels associated to each punctures. And essentially in the same way that this part can be reabsorbed in gamma, then this part can be reabsorbed in this phi here, which we call the twist function. In particular, this now is just a standard meromorphic function, which encodes all the parameters of my theory, right, into one unique object. And in fact, you can observe that the notation phi is the same notation as what I used earlier for the WKB expansion, where phi z was the logarithmic derivative of some v0. And it's not an error of my part, it's not a mistake of my part. This is, in fact, what will play the role of these phi z. And in particular, then, this will correspond to a v0 defined as follow in terms of the current. Okay, right. So that already tells us a little bit what we will have on the ODE side in this, of this construction. Okay. So far, questions? Okay.
So this fixes the part of the potential of the ODE.
Yeah, this fixes the V0 part, so the part which does not depend on H bar. The V1 will come later on. Yeah. And so in particular, the V0 part will be the same for all the states of this, all the different eigenstates of this Godin model. And then the V1 part will depend on the states, but I'll come to that. Yeah. Okay, so now what I want to explain now is some, well, not exactly results, because this will become quite conjectural from now on. Some conjectures and preliminary results about how to construct local commuting charges in this theory. And so for that, one of the main tools will be what I'll call the generalized Leibniz rule. So this is something we already saw yesterday, but let me briefly recall it. So the idea here is I want to look at what happened when I do the commutation relation of a field with a normal ordered product of fields. And that, in general, it will look as like this. So I'll get AX, CY, normal ordered with BX, plus AX, BX, CY. So this would be the standard Leibniz rule, right, that my commutator develops in the normal ordered product. But what I mentioned yesterday is that, in fact, there are corrections on top of this that come from the fact that now I use a normal ordering for the product. And these corrections are explicitly known. I don't write them because they're a bit technical, but there's an explicit formula. If we know the commutator of ABC, we know exactly how to compute this commutator of a composite field here. So another way of saying this is also what is sometimes called the generalized Wick theorem when you write it in terms of OPEs for a CFT. And so this is the kind of tools I use to do the computation that will follow. And now I need to write one of the main conjecture. So this will be kind of the important part of this section, but it will be a bit long, so please bear with me as I write it. So the conjecture states that there exists some specific field W of pzx, so that depends on p, which is an integer, and then both z and x. And they are built in the following way. So there is a starting point which is built in terms of this gamma. So this here, so if I take one gamma, I can contract it with itself with respect to the killing form, but here it's just the orthonormal basis. So I just do the contraction of gamma with itself. And then I do this p time, right? And I do the normal ordered product of all this. So
it's product of p squares, yes.
It's product of 2p terms in total.
2p terms, but each first terms are equal, yes.
So this term here, so I have in total 2p indices, but these ones I contract them together. Each pair I contract them.
I mean, without an order, 2p is p squares. First term will become p squares, and we want the first two will become p squares.
Sorry,
I mean, if you ignore all normal ordering, then
yeah.
the first two terms are equivalent, right? We have one square and second square, so
yeah, if you want, yeah. So essentially, I'm taking just I'm taking the square of gamma with respect to the killing form, right? And then I take p copies of these product multiply.
Is there some summation here?
Here, there's no summation. This is all the product.
No, summation of the a's.
Yeah. So here, maybe I forgot to say, but when I have repeated indices, I mean a summation over the indices, right? Yeah, Einstein convention, and I don't use like lower and upper indices because I am in an orthonormal basis. So I just contract them right away. So there's an implicit summation over the a's. Sorry.
But what is this normal ordering? Which I mean, what do you normal order?
Yeah, so I didn't really say exactly what I mean by normal ordering. Maybe I should have said that. So the normal ordering here mean that I essentially do put positive. I do the product of my fields as Fourier series.
Okay, so it's normal ordering in this index.
And so I put the positive modes on the right, the negative mode on the left.
Okay.
So actually, it's not exactly that. That would be the normal ordering on the plane. Because I'm on a cylinder, I get some corrections, which comes from essentially reordering. These are the Casimir type corrections, like it produced a C over 24, for instance, in the stress energy tensor. But there's an explicit formula of how we do this normal ordering, right? Yeah. Okay. So I get this part here. So if I think of this, if I look at the expression of gamma, this is just a bunch of z-dependent objects, and then in terms of field, these are normal ordered product of 2p currents together, right? So this is something of degree 2p in the fields. And then I will add to this some corrections, again, of some form. And so more precisely, these corrections, they will build by now also involving derivative of this gamma. So I take derivative of gamma with respect to both z and x. So let me write everything. dz beta q, dz gamma q, gamma a1, zx. So now I do normal ordering, but not only of gamma itself, but also derivative of gamma with respect to both z and x, right?
But these corrections are in what order? Can we say? Is it finite sum or infinite sum?
No, there will be a finite sum of these. I will explain exactly what constrains this correction a bit later on. Let me just write the full correction. So I add this type of term, and then in addition, I also allow some dependence on the twist function phi z and its derivative. So I get also terms like this in front of it. So everything that I can build essentially from phi and gamma derivatives normal ordered, right? And in fact, I put some constraints on this, which is that essentially I should have the same degree. So recall this was of degree 2p in the currents. So I want something similar here. So some kind of grading. But here the grading tells me that each gamma counts as degree 1. But then I'm also saying that each derivative counts as degree 1. So in the end, I will get a condition on the q plus gamma 1 plus gamma q. And this whole thing should be of degree 2p. Thanks. Right. So I want this whole thing to be of degree 2p, and essentially what that measures is the conformal dimension of my thing. So each j is of conformal dimension 1, and then taking one derivative with respect to x gives one additional dimension, conformal dimension, so then I get something of dimension 2p by this condition. And in fact, I have a similar condition on the z's, where every gamma counts as 1, every z derivative counts as 1, the twist function as 1, and derivative here counts as 1, right? And in particular, that gives me essentially a finite number of possible terms that I can write here for these type of corrections. And the last thing is the Lie algebra indices. They should be contracted in some way with some invariant tensors. So this could be the Killing form. This could be also, for instance, the structure constant and so on, contracted in some way. And in the end, what I want is that this whole stuff, they have some nice property with respect to commutation. So if I do the commutation of two of these densities at different values of spatial variable, spectral parameters, and degrees, I want this to be of the following form. So I want this to be an x derivative plus a y derivative plus a twisted z derivative plus a twisted w derivative. So how does that work? So if I have such a WP defined with some corrections, I can compute the commutator by using this Leibniz rule, right? I know the commutator of gamma. I have this kind of fundamental algebra. I take derivative of this with respect to both z and x, and then I look at commutators of composite field using the generalized Leibniz rule. This can be very complicated, but in principle, I know how to compute all these commutators here. And now what I ask is that I fine-tune the corrections such that in the end, all this becomes just derivatives with respect to x and y, and essentially derivative with respect to z and w as well, but now with these twisted derivatives, right? So what is the rationale under this conjecture? As well, the main consequence that it will have, if this is true, so the consequence of this is that if I have a gamma which is a contour in H, I define I p gamma as the integral of a gamma of the following v0z 1/2 minus p wp zx. And sorry, I should also have a x integral so I have both an x and a z integral, right? This is also dz. And then the result is that these will commute together for all degrees p and q and for all paths gamma and gamma prime, right? And the reason is, well, if I have this conjecture true, then when I integrate over x and y, of course, this total derivative, they disappear, these spatial derivatives. And then when I integrate over z and w with this specific prefactor here, well, recall that that was exactly the kind of things that was vanishing when I integrate then a twisted derivative. This was this property which I think now I erased, but which was the main property of the twisted derivative was that their integral with this weight were vanishing on this choice of contours, right? So that will be a way of producing commuting operators, commuting local charges in my theories. And in particular, then we see that there will be integrals with respect to both z and x, right? So of course, all this comes from the existence of these w's, right? And so far, in fact, so we know, for instance, w1zx, and this, it's very simple, it's just gamma a gamma A. So it's just this term without any corrections, turn out, for the first one.
Because there is no possible correction.
Yeah, there's no possible thing that you can write which have the right conformal dimension in which you can contract with invariant tensors. We also know then the W2. So this is in our paper with Gleb Kutuzov, myself, and Jörg Teschner. I won't write it because it would take more than just the table here, the blackboard. It's very long, but we know it exists, and we know it satisfies this with respect to W1 and with itself, right? And we found it.
What is the possible corrections? In this case, so this is constant degree 4, we have 4 gammas.
So you have 4 gammas. Then you can also write. You can take free and derivatives and use the epsilon. And then you take, you can take essentially the Killing form and then dx, d gamma. And then you can also, play with different things. You can have also just 2 gamma, but also phi, right? This phi, they also allow you to do other stuff. So you have like a number, like I forgot exactly how many terms you have to put, but it's still rather large, right? So you have some freedom because you can, if this W, you can shift them by X derivatives and by twisted Z derivatives, because of course this won't change these things here and the local charges, and this won't change this property. So you still have some kind of freedom to reduce the number of unknown, but even for a quartic, it's already not such a simple expression, but you can do it. And let me mention, so this is all for SU2. We also looked at some point at the SUN case, where in that case, we don't expect only things of even degrees, but we also expect a cubic one, and we also build the cubic one explicitly in that case. And then we expect, of course, that this goes on to infinity, right, to any degree. So in particular, then, this gives us the construction of these IP gamma. So these are then built in the end from essentially derivatives of Kac-Moody currents, right? If I come back to the initial expression of gamma here, I will get normal ordered products of this type of object. And of course, it will depend on the parameters ZR and KR, right, which we're entering essentially the definition of phi and of gamma and so on, right? But then the result is that these combinations, in particular dependence on the parameters, should be such that in the end, all of these things commute one way or another, right? And in particular, then we see that in that construction, we had what I said earlier, this kind of idea that was that the local charges themselves, they're built as integral over the Z variable, right? And so more precisely, these are local charges, so local commuting charges in the algebra built as follows. So I take SU2 hat K1, I take my n copies of SU2 hat Kn. So that's naturally where these things live, right? And in fact, you can show that they in fact live on something slightly smaller. They live in a quotient by the diagonal SU2. So these W, they have additional properties which makes that these I, they're in fact invariant to the diagonal symmetry here. So they live, in fact, in a coset W algebra, which is this algebra here, right? And in fact, this is interesting because from coset W algebra, we can recreate a lot of different algebras, in fact, right? So we could recreate Virasoro from there. We could recreate other things, a lot of things from there. Okay. So that's
parafermionic algebra.
So parafermionic, that would be more if you do, say, SU2 quotiented by U1. The parafermions would arise there. So that's another story, but you can actually also, it's expected that you have also an affine Godin model for this case where you do different quotients, not by the diagonal thing, but also by subalgebra in some way. You need to adapt a bit the way you define the theory. Other questions? So this essentially will be the end point of about the affine Godin model, and then in the last part, I want to discuss the spectrum and the ODIM. Yeah.
Let's say equal to 1, can you have several independent pointers?
Yeah, that's a very good question. Yeah. So the expectation is that for a given p, a given degree, you get n-1 independent charges of the same degree. Right? So that's also a difference with, say, the simplest case of KdV yesterday, where we had just one charge per degree, right? Now, in fact, at a given degree, we get n-1 of them, where n is the number of punctures. And that essentially comes from the number of gamma that you can write, essentially, of independent gamma that you can write. Yeah. Other questions? Maybe a comment as well. So this is quite natural when all the Kr are integers. Then in that case, this is essentially just a potential, right? A polynomial, sorry. In fact, we can even treat K to be non-rational numbers. We just have to be a bit careful on how we choose the gamma, but there's always choices that work, which are the so-called Pochhammer